Very well. So now that we have proven the capacity region for the discrete memoryless multiple access channel, we're going to, as usual, look at a continuous case, continuous alphabet case, and in particular, a particular form of the multi-access channel, which is the Gaussian case. The Gaussian case take on this form where the output y is simply the sum of the inputs weighted by some channel coefficients, channel gain coefficients G1 and G2 plus Gaussian noise. So in other words, if I want to draw a block diagram, the channel is simply an adder that adds signals x1 and x2 with weights, G1 and G2 plus noise, and we get Y. So these models, for example, the case where we have a transmission on the same radio channel, and because of the radio channel is a shared medium, the signals transmitted by the two transmitter 1 and 2 superimpose with different gains, so different scaling factors. The receiver adds noise due to the thermal noise of the receiver circuits, and at the end we get our received waveform y. Of course, you can think of this discrete time model as after sampling. We have already discussed this going from continuous time to discrete time for finite band signals. So in general, the continuous time model will be something like this, and these are, so we have two waveforms transmitted by the two users, and then the noise, and then everything is filtered and sampled, and you end up with the discrete time model that we treat here. Okay. So of course we have both the real case where all variables are reals and the noise is Gaussian real with variance and 0.5, or the complex circular symmetric case, which models the baseband equivalent of a passband channel. So it's typical of radio channels where everything happens around a modulated carrier at some frequency. For example, Wi-Fi uses the 2.4 gigahertz band, cellular around 2 gigahertz, etc., etc. So, and these after demodulation in baseband and considering the in-phase and quadrature component of the signals, we get a complex representation for which all the symbols are complex numbers, the gains are complex numbers, and the noise is complex circular symmetric with variance and 0. This is a concept that we have already introduced for the single user Gaussian channel. So here everything extends in a rather general way, in a rather immediate way. Each user has its own input constraint. In particular, we consider the classical quadratic constraint that for which we denote by E sub S K, the energy per symbol, the average energy per symbol of user K. And of course, it makes sense to consider, energy per symbol is related to power because you transmit a certain number of symbols per second that depends on the bandwidth. So this is essentially what is called the input power constraint. So for the real case, we define the received SNR's level, which are essentially the signal energy per symbol at the receiver, so it's G1 square E ES1 divided by the noise variance, which is N0 half. So we have, at the end, we have these expressions. And for user 2, we have the same similar expression. And we define the function C of S as 1/2 log of 1 plus S. This is the capacity of the single user Gaussian channel with the SNR equal to S. For the complex case, we define conveniently this SNRs defined in this way. So is the again the receiver signal energy per symbol at the receiver. So the magnitude square of the gain G1 times ES1 divided by the noise by the complex noise variance N0. Similarly for SNR2, and we define the function C of S as log of 1 plus S, which is the capacity of the complex circular symmetric Gaussian channel, single user with SNR equal to S. And then we can particularize the form of our pentagon region. You remember the region defined by these three inequalities. If I choose x1 and x2 Gaussian independent with variances ES1 and ES2, and I simply write down the mutual informations, I obtain this region. Okay, this region. Why? Because if I choose, say for example, x1 and x2 are Gaussian independent, and let's focus on the first inequality. Then you can work out the others. In the first inequality, we have to characterize the mutual information between x1 and y given x2. Okay, and there is no q because here q is not used. I'm just considering a fixed choice of the input distributions. Okay, so what is this? This is the mutual information between x1 and y. In fact, is gx1 plus gx2 plus z given x2. Now, when you condition on something, this something acts as a constant. So this is a constant. And we know that a translation doesn't influence mutual information. Translation by a constant does not influence mutual information. You can see it immediately by writing the mutual information in terms of the difference of differential entropies and using the fact that differential entropy is invariant by translation. So essentially, this conditioning is the same as cancellation. It means that this term is like cancelled. So after you cancel this term, because it is ininfluent, well, this is simply the mutual information between x1 and g1 x1 plus z. The conditioning disappears because once you cancel it, then x1 is independent of x2 and z is independent of x2, so the conditioning is irrelevant. And this is simply the capacity of a Gaussian channel with input x1, noise z, and gain g1, and so these with the corresponding definition of C of S, depending on whether it is real or complex, but it is simply C of SNR1 as we have defined. Okay, so we see that this proves the first inequality. Then you can do the same for the second, and for the sum, for the sum, let me do it. No, mistake. I have to add a page. Okay. For the sum, we want to compute the mutual information between x1, x2 and y, which is mutual information between x1, x2 and g1 x1 plus g2 x2 plus z, right? But now we notice that G1x1 plus G2x2 is a Gaussian random variable with variance G1 square. Let's do the complex case, just this one, because x1 x2 are independent, so the variance of the sum is the sum of the variances. Okay, so this will be the variance of this. So this is a complex normal 0 comma. Okay, so in other words, this mutual information is the same as the mutual information. I can write this as entropy of G1x1 plus G2x2 plus Z minus entropy of G1x1 plus G2x2 plus Z given x1, x2. Now you see that, again, conditioning makes this term constant, so this becomes, as usual, in every additive noise channel, we always have the differential entropy of the output minus the differential entropy of the noise. But this is, we said that this is Gaussian, so this is simply log pi e times the variance of these, which is n0 plus G1 square ES1 plus G2 square ES2 minus log pi e and 0. And so overall at the end we have log of 1 plus, and then here we have G square 1 ES1 plus G square 2 ES2 divided by n0, and this can be written as log of 1 plus SNR1 plus SNR2, which is exactly C of SNR1 plus SNR2, okay, which is this inequality here, okay? So this means that choosing x1, x2 to be independent Gaussian, we find this region. And this region is achievable. So the region is represented like this. And this was presented by Wiener and Cover, so it goes under the name of Wiener-Cover pentagon. And it turns out that this indeed is the capacity region of this channel. So in other words, even if I take the union over all possible distributions, and I take the convex solve of all these pentagons, well, this pentagon contains all of them. So I want to comment, well, this is essentially seen from the fact that you see it immediately from here. At the end, because of the additivity of the noise, we end up with, for whatever choice of the input distributions, they have to be x1, x2, they have to be independent. We end up with something like this. I mean, something like this. The differential entropy of the output minus the differential entropy of the noise. And it turns out that the best thing to do, this is fixed. The differential of the noise is fixed. So the maximum of this quantity is obtained by making the output Gaussian. So the output must be Gaussian or conditionally Gaussian given the other variable. For example, in this case, when you have the conditioning on x2 for the individual rate bounds, then G1 x1 plus Z must be Gaussian. So you see that you have these uniform upper bounds by choosing x1, x2 Gaussian. You simultaneously maximize all the boundaries, so you have a single pentagon that contains all of them. So in this special case of the Gaussian, in this special Gaussian Mach case, it turns out that the region is particularly simple. It's not we don't have to take the union over all possible product distributions and then and then convexify this strange region. We simply we simply have one single choice that exhausts all the boundaries, and the shape is like this. So I want to comment on these 2 points. We have already introduced these points as the corner points of the region, okay? And I want to comment this one. So for example, let's consider this one, and then you can do the same reasoning for the other point. So these 2 points are particularly interesting because they are points for which we can achieve the rates at this point using a very simple idea, a very simple receiver. Instead of a joint typicality receiver that tries to decode both messages at the same time, we can use something called successive interference cancellation. And this is a very, very interesting idea. So let's look at the rate here. User 1 operates at its own individual capacity, as if user 2 was not there. User 2, if you remember, this rate was simply the rate sum, so log of 1 plus SNR 1 plus SNR 2 minus this, so log of 1 plus SNR 1, and so we get log of 1 plus, and then we have here SNR 2 divided by 1 plus SNR 1. Okay? So this formula has a very nice interpretation. What happens if we consider the output and then we take G1 X1 plus Z as if it was noise? So we decode user 2 by treating user 1 as additional noise. Well, we can operate at the capacity of this new Gaussian channel. This is a single user Gaussian channel. The capacity of this will be exactly this one. Because the new SNR for this channel is going to be, so let's call it SNR2 prime for this channel by treating interference as noise, is going to be G2 square ES2, and then here we have N0 plus G1 square ES1. And then if you divide everything by N0, you see that you have exactly SNR2 divided by 1 plus SNR1. This is SNR1. Okay. So basically, this suggests that we can operate at this corner point by first decoding user 2 by treating user 1 as noise. Then subtracting the code word of user 2, because after decoding user 2, we know exactly its code word, we know exactly its message. Subtracting the signal from user 2 from the received signal, and then user 1 is decoded without any interference, and therefore it can operate at its individual capacity. So the structure of the successive interference cancellation receiver would be, first you get Y, you have a decoder for user 2, these outputs message M2 hat, then we re-encode this message, re-encode. So here we have the code word X2 of M2 hat. We subtract minus plus. Now at this point, the signal has been cleaned up from the interference from user 2, and now we can decode user 1. The result is that this decoder is much simpler than a joint decoder, because instead of searching over all possible pairs of messages, is simply used by composing together two decoding functions that are simple Gaussian single-user decoding function. This is called successive interference cancellation approach. And by the way, successive interference cancellation is done today. Is done today in advanced receivers for wireless communications. Interference, when you can use this successive cancellation and start peeling off one signal and then subtract and clean up and then try to decode another signal and so on. So this is a very realistic and practical technique that when it was found by information theorists seemed very science fictional and infeasible, because the complexity anyway was larger than what people were used to. We are talking about, these results were found in the 70s, and imagine what the technology at those times was, right? So, in fact, at that time, the standard way of treating interference was essentially treating it as a collision. If you have two signals colliding at the same receiver, it's a collision, lost packet, retransmission. This is Aloha, and or try to avoid collision using carrier sense. This is Wi-Fi, etc., etc. So these are like the practitioner approaches to do things. But it turns out that if you can fix and schedule the rates such that we are close, for example, I can schedule rates that are close to this point, and then I can use successive interference cancellation, which is much more advanced, and in fact it is asymptotically optimal in the sense that it will reach this corner point. Then it will, of course, with reversing the role of the two, and of course scheduling different rates. So we have to do another scheme will be able to operate here, and then by time sharing of these two schemes, we can operate at all points in the dominant phase by simply alternating with a certain duty cycle, a strategy that achieves one corner, another strategy that achieves the other one. And so, for example, if I want to operate, for example, I don't know, here at the equal rate point, well, I will simply alternate the two strategies, will say 50% of the time one, 50% of the time the other. And so, in the symmetric case, I can operate at the equal rate point using a very low complexity successive interference cancellation receivers. Okay? So this is a very interesting thing that is also very practical, and a lot of work has been done in signal processing and algorithms to implement the SIC receiver, which is now basically in every phone or base station, at least for certain standards. So if we compare this optimal capacity region for the Gaussian MAC with other multi-access techniques, let's see what happens. So, for example, in the case of CDMA, what is CDMA? CDMA is use signals such that each one looks like noise to the other, which means treating interference as noise, but for each user without successive interference cancellation. And in this case, then we can achieve just points inside this region, because this is the rate for user 1 treating user 2 as interference. This is the rate for user 2 treating user 1 as interference. Without successive cancellation, each one treats the other as interference. So the receiver is very simple, but you see the rate region is greatly reduced. If we use orthogonal access, so interference avoidance, well, we can get the time sharing of these individual capacities. And it turns out that if we use TDMA, but taking into account that if we use, with the fraction lambda, only user 1 transmit, and if we use with fraction 1 minus lambda, only user 2 transmit, then the average energy per symbol, well, is not, it gets reduced, because I say user 1 will be active only for a fraction of lambda of the time. So at the end, we can, while we are transmitting, instead of transmitting ES1, we can transmit ES1 divided by lambda. And instead of transmitting ES2, we can transmit ES2 divided by 1 minus lambda. Because we use, so we can use a larger energy per symbol when the user is active, because then the user is idle for a certain time. And so on average, over time, so if we can actually afford, so instead of having like a peak energy per symbol, we have a time average energy per symbol constraint, then it turns out that with orthogonal access we can do a little bit better. We can do something like this, and this region will touch the dominant phase in one point. So there is like an optimal choice depending on the gain, so depending on the shape of the pentagon, there is an optimal choice for the duty cycle lambda that achieves at least one optimal point on the dominant phase. But however, orthogonal access is suboptimal because, for example, the pentagon is generally a bigger region. There are rates, for example, these two corner points typically cannot be obtained by orthogonal access. Okay. So we can also generalize these results to k users. This is a very good exercise to do for the proof. For the discrete case, we have this theorem. Is not very difficult to prove. It follows along the same line as for the case of two users. The capacity region of the k user discrete memoryless MAC is given by the union of all the rate regions defined by these inequalities. So these inequalities is for every subset calligraphic k of the user index set, we put some the inputs in subset k here, and the input in the complement subset in the condition. Okay, and then this union is over all possible joint distribution given by this product form. So it's PQ and then the product of all PXK given Q. So you see that this is the generalization of the case of two users, because in the case of two users, the subset K can only be 1, 2, and 1, 2. And so we have, at the end, we have only 3 inequalities here. The inequality for rate 1, inequality for rate 2, and inequality for the sum rate. In general, if there was, for example, for the case of 3 users, well, we would have inequalities of the following type. We would have R1 less or equal than mutual information between x1 and y given x2, x3. And then you have all the other 3 inequalities for the individual rates. Then we have for all possible sums of 2, R1, R2, less or equal than mutual information x1, comma, x2, and y given x3 and q. And then for all possible pairs, so we have 3 inequalities like this. We have all possible 3 choose 2, so another 3 inequality like that. And then we have the inequality for the rate sum, which will contain the sum of the 3 less or equal than the mutual information between x1, x2, x3, and y given q. Okay. So same here. So for the Gaussian case, everything generalizes to the k user. So we have now the sum of k users here in the signal, right? Each one has its individual energy per symbol constraint, and the capacity region is given by the region defined by these inequalities. So you see these inequalities again come from, they are exactly the same as the case for 2, but now we have, how many inequalities we have? Well, all possible subsets, non-empty subsets of the user set. So in general, we have always 2 to the k minus 1 inequality. For example, for the case of 3, we have 3 individual rate inequalities, 3 sum of 2 rate inequality plus 1 sum rate, so it makes 7, and so it's 2 to the k, 2 to the third is 8, minus 1, 7. Okay? Those are all possible subsets, non-empty, of a set of k elements. Okay? For every subset, you get an inequality involving the rates in the subset. So I want to finish with this by showing you the region, the generalization of this pentagon in 2 dimensions. When you go to 3 dimensions, we get a region of this kind. And now we have a lot of corner points. So this is still the dominant phase. And we have all these vertices. Let's mark them in blue. We have these vertices. Now, how many vertices we have? Well, it turns out that we have exactly, in this case, 1, 2, 3, 4, 5, 6, which is 3 factorial. In general, we have k factorial vertices. And this k factorial is not by accident, because if you remember the successive interference cancellation that I was mentioning before, well, it turns out that successive interference cancellation depends on the order in which we decode the users. And for every order, so for every permutation of the users, we have a different successive interference cancellation rate tuple, and all of them correspond to vertices of the dominant phase. So we have k factorial possible permutations, and we have k factorial vertices. In the case of 2 users, we have only 2 possible orders, 1, 2, and 2, 1, and then we have 2 vertices. So we stop here, and then in the last part of this chapter, we talk about the problem of resource allocation on the Gaussian MAC that uses critical properties of the shape of this region, which is called the polymatroid. And this is a very important, say, combinatorial polytope with important properties that allows to solve resource allocation problems that we will define in an efficient way for the Gaussian MAC.